Hi all. Let's start with our next session of this module. Kana maps. In simple terms, normally we will be calling it as a K maps. Most of them you might have already heard about it. K maps, Kana maps. Okay. Basically, this will be used for simplifying the input-output combinations conditions, and it's a very well-known map. It will be represented using a 4x4, 3x3 matrix. So, and, let's go deeper into that and try to understand. So, what happens already in the previous session, we have seen some of the procedures, Boolean algebra rules that we have seen already. So, let's assume that. So, it will be easy when you have when a minimum number of input combinations. Suppose if you have more number of input combinations, then definitely it's a task, pretty tedious task to do that. So that's a reason, and that's one of the reason. Uh, and also at whatever the expression that you get at the end, it's not still it's not sure that whether whatever you have obtained is a minimal one or the last solution for it. So in order to overcome such scenarios, we are going for Karnaugh maps. Karnaugh maps. The Karnaugh map method or the Quinn-McCluskey procedure used to overcome these difficulties by providing the systematic method for simplifying the switching functions. Karnaugh map is useful tool for verifying, simplifying, and manipulating switching functionalities of 3 or 4 variables. That means 3 or 4 inputs. Okay. When a function is realized using AND or OR gates, the cost of the realizing function is directly related to the number of gates. That means suppose if we have more number of inputs, then the cost of implementation will be dependent on number of inputs. So if the input increases, definitely the cost of implementation also based on the input increases. The Karnaugh map technique is developed that lead directly to the minimum cost two-level circuit composed of AND and OR gates. So whatever the solution that we obtain at the end, using that we can implement a simple logic circuit which will give the exact output which we want to have it as per the truth table and as per the expression. And let's see like how it goes in further slides. Let's assume that a sum of a product of some expression corresponds to the two-level circuit composed of uh, OR gates feeding a single AND gate. That means we may get, suppose if we have more number of inputs also, we may result in two AND expressions and one OR gate. So that we need at the end only we need 3 inputs. Okay, therefore to find a minimum cost level 2 AND OR gate circuits, we must find a minimum expression in the sum of products of sum. So it is nothing but a simplified expression, so we need to find it. The reason is has a minimum number of terms, and all of those expressions which we have the minimum number of terms has a minimum number of letters, and we need to resolve it like how sometimes suppose even though if we have many number of inputs, what happens after simplifying we may end up with only having a 2 inputs. That reduces overall gates required and number of inputs required. So it will have a direct impact on the implementation of that logic circuit. A minimum number of gates and minimum number of gate inputs. That's what I said, like it can have a cost impact. So given a function may have two different sum of product terms, each with the same number of terms and same number of literals. It can happen like that. So given a min term expression, the minimum sum of products can be often obtained by following procedures. So as you already know that using this one, combine the terms using the uniting term, where we already know that AB bar plus AB equal to, it is nothing but A only. So suppose if we do this repeatedly, it will eliminate many literals. Here you can see we have nearly having a 4 inputs and we have only got a one single output. Okay, x plus e1, and also we know that there may be we might be having a possibility like x plus x, and know that suppose if we do the function, so only one output or only one input, only one result will be getting across to get a x. In the simple terms, what we can say, in order to reduce the redundant terms, we may just will be using this one. So unfortunately, result of procedures may depend on the order in which terms are combined or eliminated, so that the final expressions obtained is not necessarily a minimum. That means, suppose if we have nearly a 5 terms, like how we group the 5 terms, even that's also matters. Which functionality we are trying to apply it at the first, which logic you are trying to apply it at the first, even that also matters. To get rid of it, we are going for k-maps. Okay, so let's assume that we have this min terms. Here you can see, and as per this, one minute, let's one minute, last view. Here I can see we have nearly a we have only 3 inputs, and nearly 6 possible outputs as a one. Okay, uh, yeah, minimum expression for a function is defined. Expression for a function is defined as a product sum of term. That means if we know that already ABC, A bar BC. So in that terms, we may need to define it as a min term, has a minimum number of terms, and all of those expressions which have the same number of terms has a minimum number of literals. Unlike max term expansion, minimum product of sum form functions, minimum sums form of a function is not a necessarily unique. That means whatever will get at the sum SOP, at least it will be a unique in nature to some extent, but it is not necessarily the same in terms of SOP. Okay, minimum, here you can see minimum product of sum can be often obtained by uniting the theorem, and this also we know that, but x plus y into x plus y bar equal to x. These are the algebraic notation, like how we used to represent. Already we know that any variable with a bar, it indicates it's a 0, directly a variable or a input time it represents as 1 itself. So that here you can see AB bar CD can be represented as 1010. Same here also, you can see the same results here. Okay, note that the min terms only combine if they differ in variable, and the products only come. Okay, minterms only combine if they differ in one variable, and the products only combine they have dashes or the same differ sorry differ in one or other variable. Okay, so let's come to the k-map directly itself. So let's assume that these are the two inputs. Here you can see these are A and B. We will be having A will be having two status, and B will be having two status, 0 and 1. 0 and 1. So if we want to put a 0 0 combination, A is 0, B is 0, so we have to place it here. Here you can see it has been represented clearly, A equal to 0, B equal to 0. Suppose if we want to put A equal to 1, B equal to 0, A is nothing, A1 comes here and B1 and B0 comes here. Here we need to place that value, and same applies to 0 1 and 1 1 also. And this is the example of truth table. Already you might be knowing how we will put it. 0 0 for the A as a 0, B as a 0, we need to place it 1 here, and 0 1 also we need to place a 1 here. And here you can see the complete picture, like instead of suppose if you want to solve it this one, you may have to read many steps to get a result, but in the simple terms you can see we are trying to get a result here. And how it can be written, so it is nothing but A bar 0 is nothing but A bar, here 0 is nothing but B bar, A bar B bar plus, it's a bar, right? A bar column and it's a B. So it can be written like this also, the final expression what we used to happen, what we used to get. And it can be the combination or like four type, it can be grouped into four types basically. One is a single, and then is a second one is a pair, and fourth one is a quadret and octet. So here you can see, and while grouping, always the ones we will try to group a one, and always it should be next to each other. Here you can see if we if we group this one here, what it says, only we will get a 0. How we will get only we will get a bar if you try to resolve it here. So this is the expression what we have got. We already know that a bar b plus a bar b bar, ab plus a bar b equal to a. Here we have a bar b bar, that is nothing but a bar. So still if you want to understand, here we'll be having b bar and b. So b and b bar cancels each other, only we will be left with a bar. So this is how it happens. And here also you can see two variable maps. So for 2 and 3, how it can be placed. Suppose if you want to write it in terms of a 1 to 0 1 2 3 4 combination, here you can 0 1 2 3 combination, it can be written like this. And even if you want to interchange the variables also, the result will remain the same only. Here what is the difference? Here you can see a has been placed here, b has been placed here with that, but here you can see the output has been changed. It has been shifted to 2 and 3 here. So 2 and 3, 0 1 2 3, right? Suppose we have to place it in 2 1 3 combination. 2 1 3 combination has been placed. Now this can be grouped as a pair. So we know that b and b bar cancels with each other, and the result only we will be getting a here. And that is with respect to our two combinations. And this is now, suppose what if happens if we have three inputs. Here you can see how it can be grouped. So one side we will be having only one variable, and in the other side we will be having two variables, and we will try to configure with the remaining. Like here we will be having a bar and a. Here we will be having b and c, right? 0 0 0 1 1 1 1 0. It's not 1 0, and we'll be having in terms of 1 1 1 0. Why we need to have always why we need to have 1 1 at the first and 1 0 at the end? It matters seriously. It's called gray code. Like unique number should change always. That means if you observe it here, only one number has been changed here, and if you observe it here, only one number has been changed. 0 to 1 transition only happened. And if you observe it here, only one number has been changed. What if happens if we place it here, 1 0 here and 1 1 here? So 0 1 0 becomes 1 0. That means completely a two number change will happen. So which may lead to some other distraction in the Karnaugh map. So it is not supported, and recommended to use 0 0 0 1 1 1 1 0. This is the combination. In this combinations only you have to use. And let's see. And for this combination, a b bar c, a bar b bar c. Okay, a bar it comes, b bar c, a bar it comes. Okay, sorry, let's this one, right? A bar b c bar, a bar b c bar, in the sense 0 1 0 0 0 0 0 0 0 0 0 1 0 1 1, sorry, 0 0 0 0 1 0 1 2 3 4 5 6 7 0 0 0 0 1 0 1 0 0 1 1, like this it goes. That's it. And now where we have to place 0 1 1, here only 0 1 1 we need to place like this. We have to do it, and we will try to fill all the possible combinations, and we will try to get what is the result here. The pictorial representation has been placed, and in the next slide we will try to group it. like this is how it happens. Adjacent cells we will try to get counted here. That's what I explained. It will be 0000001 0 1 2 3 4 5 6 7. Okay, suppose, okay, now we will try to put 267 into a K map and see how it will look. So this is what we have in the, this is a truth table representation of it. And as we already know that it's a 3 input combination, since we have a 7 here, so it will be a 3 input combinations. And how it will come, so here you can see we are having 0 1 0. These are the 3 places that where we have to mark it. Okay, A bar, B, C bar. Okay, will come here. A bar, B, C bar. Okay, we have to mark it 1 here. And A, B, C bar. A, B, C bar. Here also we need to mark a 1 here. Here also we need to place. And this combination is having output as 1 here. And ABC also, here also we are having a combination as 1 itself. And we will try to have it for max terms also. So max terms already you know that, so the output we will be considered where we are having only a 1. So, and let's try to get it for only a 3 first combinations 1 3 5. Okay, we already know that 0 0 1 and 3 3 0 1 1 and 5 1 0 1. In these combinations we need to place, and these ones will be considered for SOP and remaining will be considered for POS. And how we'll configure, how we'll group, this one matters. As I said already, quad is nothing but 4 combinations. We'll be considering 4 ones together, so and it will be set as a quad. And the always this number should be adjacent, and it can be rolled also. That one we need to consider it here. Here you can see how this has been taken care. Means if we fold this one, if we fold this K map in the vertical direction, this will come adjacent to this, so that this can also be grouped. Okay, and if there might be one question might be running in your mind saying that, is there any possibility that a number can be grouped again more than one time? Yes, yes, we are having a option of doing that. Here you can see, in order to simplify the terms, so this can be grouped once, and instead of grouping as a one single variable, since we are having a 1 at the adjacent cell, it can be grouped again with the 1, even though it has been already grouped. So after simplifying this, if we take B bar C as a combination, B bar C as a common terms here, A plus A bar is always equals to 1. So it will be ending up with getting B bar C. And in the previous slide, I already have mentioned that we can group more than once that 1 here, but does it make a sense? Can you observe it here? Does it make a sense to group more than 2 times here? Because it can be grouped more than 2 times also, but this is not a valid, right? Because instead of grouping 3 here, it can be grouped 2 only. Already this has been taken, because these 2 terms, it doesn't make sense because it has been already captured. Suppose if it's not captured, if any term was there here, or if any term was there here, so it could have been taken like this. So instead of doing that, it's called as redundant groupings. We should not do redundant groupings to get that, and always we should try to have some uniqueness while doing it. And this is one more, already you know that, so how it can be placed it here. And if you group it exactly like it can be grouped like this one, like this. And also it can be grouped in different way here. Here you can see the same truth table and the same K map has been used. So like this. This is a one combinations. So nowhere is it is repeated. And suppose if you want to do it in other way also, we have one more option. These two can be grouped. These two can be grouped. And when we fold this, we will get one more combination. That's what they have placed it there. And already we in the last session we have discussed about don't care terms also, right? Don't care is nothing but we we can have either 0 or 1, so that don't care, it depends on your flexibility. Don't care can be considered. Okay, it is required midterms are indicated once on the map, so don't care midterms are indicated by X. When choosing terms to form a minimum sum of products, all the ones must be covered, but X are only used if they will simplify the resulting expressions. That means we already know that it can be a 0 or 1. Okay, in order to simplify the term, we can consider or we may not consider, it is left to us. But when we will try to consider don't care is when you have an option of more simplifying possibilities. That time only we have to use don't care conditions, and we'll here you can see. Okay, here it's a best example like how it can be done using don't care conditions, and we will try to have it. So we will try to have it for F. And these are some of the problems that you may have to work on it. And it will be good if you work on more. So if you how much you know about the K-map, it will be very easy for you guys to do get settled in K-map, because it's a very useful topic when it comes to digital logic circuit. And 4 variable K-map, let's start with that. So till now we have seen 2 variable K-map and 3 variable K-map. So let's move into a 4 variable K-map. Already you might have seen, expect this. Let's assume that we don't have a B here. You might have 3 variable combination. That means these two will not be there. Like it will be there. Only 8 cells will be there. What if happens 4? So we will try to group two variables, different two variables, and we will try to have it like this. So already I have explained 0 0 0 1 1 0 why it's a gray code. So it offers only one one code change while moving from one code combination to next input code combinations. Here I can say 0 1 2 3 0 1 2 3 4 5 6 7 4 sorry 0 1 2 3 4 5 6 7 and 8. It will not start here, it will start from here 8 9 10 11 12 13 14 15, and this is a decimal representation of that. So as it has a 14 and input has a 4, we'll try to have K-map for this. And if we try to have it, we can see for 1 we are having a 1. Here you can see this is a decimal representation like how it looks, right? So for 1 we need to have a 1 here, and which is 1. This is for 6 we need to have a 1 here, and the 7 we need to have a 1 here, and 14 we need to have a 1 here. So this is how we have to place true type variables into a K-map in 4 variable K-map. And how it can be done. So already I have explained you one thing here. So it can be folded like this in vertically or horizontally also. There is one more possibility that it can be folded in a different way. That means this corner can be folded with this, and this can be folded with this. That means all the 4 can be always all the 4 also can be sorry, all the 4 can be combined together. Here you can see, so we have a 4, right? So it can be configured like this, it can be grouped like this, and here also only we'll be ending up with only 2 terms. And already I have told you about octet here. And I suggest you to do one more things. You guys try to have this in your, try to do more work on this, try to put these numbers into K-map and see like how it comes and how it will happen. Okay, and you will get a more idea instead of explaining it in the PPT. And this will be having one quad 4 combinations and maybe the one pair combinations. And here you can see we can have a octet here. That means 8 possible combinations can be grouped here, one itself. and all the corners we have 1 1. That means if we fold like in a 4 step, okay, 1 2 3, if we fold 4 times, so we will get all the corners at the one end, right? 1 2, if we fold 2 times, if we fold 2 times, one time what will happen, this will come on this, and once again we will press on this, so this all four one will come on one corner, so all four can be grouped like this. 1 minute, sorry. All four can be grouped like this, and also we have one left with a one pair. So, and if we combine this one, what happens is, here you can see this all the combinations present here, it goes off. And here also, what is the D, right? 0 and 1 we have, it goes off, only it stays with a C it stays with. And here you can see it will be A bar BD, so it's A bar B it is, and here you can see C bar cancel, so it will be D. And for this one, this all four terms, if we group and simplify it, it will be a B bar D. And how we will consider don't care condition. This is a beautiful example you can go through, because you can see some of the combinations we have considered, some of the don't cares we have considered, and some of them aren't, because so we can group. So what happens is, like, it can be grouped as a quad, okay, and this one will be left as single, or we need to take a pair of this. Instead of that, what happens, it can be considered as a quad considering the don't care condition, okay. And this way we are not considered, because it doesn't matter, right? It can be a 0 or 1, so we wanted to simplify it. That's the reason we have considered here, and the other condition we are not taken into consider, we are not considered for it. And here you can see sorry, here we are trying to have it for product of sums. Previously already we have seen it for sum of products. Now we are trying to see it for products of sum. Sum of products, how it will be represented, F will be represented with a summation. But how products of sum will be represented? Product of sum will be always represented with F bar, and output we have to maintain F bar will be displayed, and results will be considered as 0 here. And let's try to identify it, like how it works. And how it works, here you can see how in this one, how they have trying to configure it. One thing here you can see, all the terms here will cancels each other. It will be a y bar z. They have considered it, they are considering it for zeros. If they're considering it for 1, directly they would have mentioned F there. So here what happens, here Z cancels, so 0 and 1, Y will stay. So Y into W bar X, Y into W bar X. This is the one term you can see. And here what happens, Y 0 and 1 is there, it will cancels with each other. Z we need to have Z0 we need to represent, so it will be Z bar. So X W X Z bar, here you can see. And this is how we have did, right? So we need to convert this one into, this is in SOP form, we need to convert it into a products of some form. How it will be done, means, always we will put a one complement symbol here, and we will try to have it. So complement of Y, and Y whole bar it vanishes, so it will be a Y, and functionality will become or functionality will become and functionality. That's how it works. And this is the end of a session, beautiful session I can say, and it will be very useful for you guys, and please try to make use of it. Thank you.